Today, the physical properties of silicon are the primary constraint on AI speed. Modern chips are pushing against the absolute ceiling of thermal dissipation and the data transfer limits of the memory wall. To navigate these physical boundaries, the computing market has introduced a range of specialized hardware: CPUs, GPUs, TPUs, and NPUs. Choosing the wrong architecture for a specific project has immediate, measurable costs. It can inflate cloud budgets, throttle throughput to a crawl, or drain edge batteries in minutes. Optimal performance requires a calculated trade. To get the best results, you must sacrifice general-purpose flexibility for high mathematical specialization, dictated by where and how you plan to deploy your model. Look at the room-spanning scale of this early ENIAC system. This tangle of physical cables established the foundation for the programmable electronic brain. John von Neumann eventually proposed a model that stored both data and instructions in the same memory. This created sequential processing, fetching, decoding, and executing instructions one at a time. By 1971, that entire room of infrastructure shrunk into a single chip. The modern microprocessor became the primary orchestrator for the whole system. Today's central processing units, or CPUs, dedicate a large portion of their silicon die to deep cache hierarchies and branch prediction logic. They are engineered to navigate complex, non-deterministic tasks with high speed. This diagram shows what happens when that sequential design meets AI math. A single matrix multiplication requires roughly 2 billion simultaneous arithmetic operations. Trying to process that through a CPU creates a data bottleneck that stalls the entire pipeline. The CPU remains a vital orchestrator for operating systems and data preprocessing. However, to execute the heavy math of neural networks, it must offload tasks to specialized accelerators. The graphics processing unit, or GPU, trades sequential logic for parallel throughput. The GPU uses a single instruction, multiple threads architecture, or SIMPT. It distributes work across thousands of small cores, executing operations simultaneously. For matrix math across vast datasets, this parallel structure is the standard for training models. That throughput requires significant infrastructural investment. GPUs carry high acquisition costs and demand intensive electrical power and complex cooling systems to manage their thermal output. GPUs are the high-throughput engines for AI training, provided the deployment site can manage the energy and cooling overhead. For global cloud workloads, Google developed the Tensor Processing Unit, or TPU. This is an application-specific chip designed strictly for deep learning operations. The TPU utilizes a systolic array microarchitecture. Instead of constantly writing to a central memory bank, it passes results directly between neighboring nodes in a continuous wave. This minimizes power-hungry data movement, delivering up to 4.7 times the performance per watt. The limitation is flexibility. Using a TPU requires committing to specific software ecosystems, like XLA or JAX, and the chip cannot be used for any tasks outside of AI. Cloud architects choose TPUs when they are ready to trade software flexibility for higher operational efficiency at scale. On edge devices like laptops and phones, the priority shifts to the Neural Processing Unit, or NPU. AMD and other manufacturers are now integrating these directly into their consumer product stacks. NPUs use spatial data flow architecture to execute operations entirely on a low-power processor. This allows the chip to run AI tasks locally without communicating with off-chip memory or external cloud servers. To achieve this efficiency, NPUs utilize quantization. By reducing mathematical precision to int8 or int4 formats, the chip gains significant speed and power efficiency. This enables features like live background blur or local language assistance to run on single-digit watt budgets, ensuring user data stays strictly private on the device. While an NPU cannot handle model training, it is the most efficient silicon for delivering always-on, privacy-safe AI to everyday consumers. This decision flowchart maps the deployment location directly to the necessary architecture. On the cloud branch, prioritize GPUs if you require broad framework flexibility. Migrate to TPUs if you need high-throughput matrix math at an enterprise scale. On the edge branch, prioritize NPUs to ensure local AI features don't compromise battery life. In all scenarios, the CPU remains the necessary top-level orchestrator for the operating system and data ingestion. Matching the processor to your operational requirements is the only way to prevent a hardware choice from strangling a project's budget or performance. The future of computing is heterogeneous, with multiple specialized chips working in tandem. Cloud providers are already combining CPUs and GPUs on a single substrate, while new laptops integrate CPUs, GPUs, and NPUs to handle different parts of the workload simultaneously. Competitive advantage now relies as much on the specific silicon architecture as it does on the software models being deployed.